Is V2 3 or negative 3? I know you get the exact same answer either way, but what is V2 3 or negative 3?
3.
Why?
Rod vector.
Right.
Okay.
What?
Doing the fancy math, we get 40 plus 9. Units?
Joules.
All right, so K final, 1/2 times 5 times 0 squared plus 1/2 times 2 times 7 squared. And you go through the fancy math, and you get 49. Now, in terms of the problem on the last test, I'm not going to specify which technique to use. So again, if you've already done the practice with one of the other techniques, stick with it if that's what you like. And then if we did what I believe to what Dylan was referring earlier, the Newton's cradle,
Yes.
if you go through that analysis, if I bring one up and it comes down, then one will come up here. That is because momentum is conserved and kinetic energy is conserved also. Ish. So in that Newton's cradle, I'm assuming everyone knows what I'm talking about. That I'm getting mostly nods. How do you know energy cannot be conserved? In reality, I mean, it's close and that's why it works, but how do you know that there is some energy loss?
The sound?
Yes. Also, the balls probably heat up just a little bit too, but that's a lot harder to detect. Oh, any questions before I erase? That at least. Looks like somebody replaced some of these markers. All right, let's shift gears. I did the door before. That really is not convenient. Let's stick with it. That's right. I've already looked at that. That doesn't rotate. There we go. I want to spin the chair. How do we do it?
Push it.
That didn't work. I know, I'm taking something that everyone here knows how to do. I usually do opening and closing the door. If the door went this way, I would definitely be using the door right now. But as physicists, what we're doing is we're taking an everyday thing and we're basically overanalyzing it. So, I've done this exercise with how do you tie a shoe. There's a half hour. All right, so pushing it is not enough.
You have to push it at an angle. Well, don't push it yet. At an angle. You have to take it and you have to you know what I mean?
Take the edge of it? and
Yeah, take the
slip
edge of
around.
it and make a circle.
And push perpendicular to your body.
So, perpendicular to my body?
I don't know how that works. Yes.
You don't know how to spin a chair?
Physics.
I'm not sure what perpendicular to my body means. My
If
body
your
is,
body's facing one direction, then
So,
you would
all right.
shove it
My
to
body's
the
facing
left
that way.
or the right. Yes.
so you consider my body is in that direction,
Yes.
so perpendicular to that direction.
Yes. And then you would push it to the left or to the right on the edge.
But not
of
the whole
back.
chair, just the seat.
Oh, all right, so I'm gonna push the seat left or right
From the back of the.
Yes.
from back here.
Well,
From the side of the back.
have you
That's
watched?
back.
Yeah, there you go.
There.
Have you watched that one episode of SpongeBob where he's talking about on the lid?
Yeah.
Oh.
The lid?
No.
Oh. It's good.
Oh, no.
You should watch it.
Have you heard the Carlin routine about getting on an airplane?
No.
He said, I'm not getting on an airplane, I'm getting in an airplane.
Mm.
All right, so pushing from the side, left or right?
Yes.
Yeah.
Oh, I guess that was a pull. Pulling doesn't work,
It could.
I mean,
Okay.
yeah, it could.
but
yeah.
you just want me to push.
It would be easier.
All right,
Wow.
I know. So why pushing on the backside?
Physics.
Because you can't push on the front. I mean, I guess you could, but from what your perspective, you can't really. Well, you could still push on. Yeah, you could.
So-
Yeah.
Yeah.
But what's so special about front or back? Why does that not, I guess that one work too. Why does that not work as well?
Because you're pushing from the center of the
Why?
mass and not
What
the edge.
difference does that make?
Well, because if you're trying to spin it, then you need to push the edge of it, not the whole thing.
All right, let's take the door. If I push on the edge, that it's gonna open or close?
Which edge?
And so the edge matters, okay?
Yeah, it's like in respect to the hinges or to where the spinny thing on the chair in the middle of the.
All right, so
the
first
seat
let's
part.
say the vocabulary word here. Axis of rotation.
In respect to axis of.
I will sometimes call it the pivot point instead of axis of rotation. Properly, axis of rotation is, I guess, more pedantic, but. Okay, so. So describe how the push should be relative to the axis of rotation.
Perpendicular to it?
The axis of rotation is vertical here. So as long as I'm pushing horizontally, it should rotate.
Like along the edge of the,
I'm pushing on the edge, it doesn't spin. I think all of you very clearly know how to spin a chair.
Yeah.
Like, how does the push to be most effective, or actually, let's do it the flip way. How would I be least effective in pushing it with respect to the axis of rotation?
If you push like towards the center.
Okay, but towards the axis.
Yeah.
All right, so if the push is towards the axis, it's not particularly effective. Pushing away from the axis, what about that?
Effective.
It is effective?
It is.
Maybe not.
You have to like, I don't want to sound stupid.
What, you have to spin it?
I mean, no, you have to, I guess, spin it around the.
To spin a chair, you just need to spin it.
I mean,
That's what I'm
yeah,
getting.
but-
All right, let's we'll get back to this, but, so if I want to spin it fast, let's assume that I know how to push and where to push. To spin it fast, what would I need to do?
Push hard.
Okay, so in order to spin it, obviously, force matters. The direction of the push matters. And I guess where I push matters. I think that pretty much sums up what I have. So we need to somehow deal with these three things in a nice, neat formula. There is an additional vocab word that, for some reason, was escaping you. Moment arm. Some textbooks will call it the lever arm. And the moment arm or lever arm is a vector from the axis of rotation to where I'm pushing. So if I do an overhead view of the seat, actually, let's see if I can at least come up with something pseudo-realistic. This is the back of the chair here. This is my axis of rotation. If I push on it, however I push on it, if I push on it like this, that's where the force is applied. The moment arm is a vector from the axis to where I'm pushing it. That is the moment arm, typically symbolized by the letter R. And this would be my force. If I'm talking about the door, let's see if we can get one more clue here. If I'm pushing on the door and I want it to open, where would I push on the door to be most effective?
The farthest away from the axis of rotation.
So the bigger my moment arm is, potentially the more effective it is. The farther I am from the pivot point, as long as I'm still on the object, because I could push back there, which would give me a really long moment arm, but not particularly effective. Just demonstrated right there. It's one reason they put the handle over there.
So Hobbit doors are not very effective.
No, actually, it just seems like a poor design. So, but the other thing is, if I'm looking at the chair here, if I want to get as far away from it as possible, or close to it, the back of the chair is pretty much as far away as I'm going to get. My axis of rotation is somewhere around there. If I push directly on it, well, my moment arm is a vector going from there to here. Really can't get much larger on my moment arm. My force, still not causing it to turn, so somehow I have to take direction into account. And the math people have come up with a way. Cross products. Cross product, as opposed to the dot product. A dot product is a multiplication that you get, such as when you're finding work. It's force dot displacement. Now we are dealing with a cross product. What are you going to guess is the symbol that we're going to use?
Across.
Yeah,
Okay.
it'll look like an X,
Okay.
but yeah, it's basically, it's a cross. So the formula I'm looking for here, R cross F. Unlike dot products or scalar products, well, let's come up with a distinction between the two. So we have dot product, and then cross product. Dot products are also called scalar products because you get a scalar in the end. These are called vector products. Anyone want to take a wild guess why they're called vector products?
They're products.
Sorry?
Their direction.
Yeah, or more generally,
Their products equal, think vector.
yeah. These are also called inner products. And outer products. The last pair is not something that I'll spend much time in, but if you get far enough in math, you'll get to eventually inner products and outer products. I think these are much more generalized terms as opposed to what we're dealing with here. All right, so let's talk about, since my cross product right there is a vector, how do you actually find the direction? Well, we've talked about this some when I had the wheel. I think it was this group. If I have a wheel spinning around like this, what is the direction of the angular velocity?
This way.
Yeah. Using the right hand rule, the velocity is in that direction. If I have a door here, and I push on it like that, there's my force. My moment arm is a vector from here to basically here. What is the direction of the cross product? Which way would the door spin?
Down.
Not down, or
Like upwards?
outwards.
Yeah,
So if you push on a door like that, the door is going to spin like this.
like upwards.
Is it up?
Think, but a hinge right here. First off, clockwise or counterclockwise?
Clockwise.
All right, I think we're in agreement there. It is clockwise. Remember when you're determining the direction, thumb points along the axis, so it's that way or that way. Fingers point in the direction of the spin, or the desired spin. I can still apply torque clockwise or counterclockwise and the door not move, such as when it's latched. So you can figure out the direction of this R cross F based upon the right hand rule, or there's an alternate. So I have R going this way, I have F going this way. If I'm doing a cross product, I put my fingers in the direction of the first vector, so I got basically 360 degrees of freedom there until I bring in the second vector, and I want my fingers to curl in the direction. The quickest way to get to the second vector, my thumb points into the board here. So this R cross F would be into the board. And as I said before, there's nothing actually going into the board. This is just a math notation. And it makes life a little bit easier if you are paying strict adherence to the math. Now, you can't have a physics equation without giving it a name, and of course we give it a name. This is torque. Or G2 Kabuka.
Say that again?
G2 Kabuka. I will not explain that reference, but it is one of my two most obscure references that I will ever make in this course.
Please hold. So the symbol for torque is a T with a squiggly line on top?
It's a cow. Yes, it's basically, it looks kind of like a T except you squiggle the top. This is a tau.
T-A-O.
Typically,
Is this Japanese or something? Or Asian? Like
Greek.
Greek. Definitely seems Asian.
There's the TAO, which is a Eastern religious thing.
Taoism.
Also, I pronounce it the same way. I'm sure there's a distinction in the way it should be pronounced. So torque is this R cross F. Now, let's think a little bit about what cross product means. If this is a door, overhead view of a door, and I push on it that way, it's gonna, that force right there is gonna cause a torque into the board. That's sort of the language that you would use. Because this force right here wants to rotate the door that way. If I took my door, overhead view of the door again, and I push on it this way, right into the edge, my radial unit vector, or not radial unit vector, my moment arm is a vector going that direction. But here, my torque is 0. So there's obviously a clear distinction between these two, and this is bundled up in what we're calling the cross product, because dot products care about parallel. You basically multiply parallel components. Here, you multiply perpendicular components. None of the force is perpendicular to the radial moment arm, so therefore no torque. If I have an overhead view of the door, I'm applying a force at some angle like that. My radial unit vector, my force. The parts that I'm multiplying between the force and my radial unit vector is the component that is perpendicular to it, because I can break force up into components. The part that's parallel does absolutely nothing to the torque. The part that's perpendicular is the part that will actually get it to rotate. Since I multiply perpendicular components, let's sort of rewrite them tail to tail. So if I have my R and my F, and I have some angle between them, theta, I want the perpendicular component of F the perpendicular component is just going to be my hypotenuse times the sine of theta. So this becomes F sine theta. So I can somewhat generalize that the magnitude of R cross F is the magnitude of R times the magnitude of my force times the sine of the angle between